Welcome to this online presentation for SIGCOMM 2020 paper, Leveraging Ambient LTE Traffic for Ubiquitous Passive Communication. My name is Zichen. I just got my PhD from University of Maryland, Baltimore County, and will join Cleveland State University as an assistant professor very soon. This is a joint work with my colleague Xin Liu, Wei Wang, Yao Yao, and my PhD advisor, Ting Zhu. Backscatter, especially ambient signal backscatter, is a promising future for Internet of Things devices. In backscatter communication, a backscatter device takes the ambient RF signal in the air as an excitation signal and piggybacks new data on these signals. Without directly generating RF signals, backscatter can conduct wireless communication with as little as tens of microwatts power consumption. Ultra-low power wireless communication is the most attractive feature of backscatter. With ultra-low power consumption, backscatter devices can even achieve maintenance-free communication. It eliminates battery charge or battery change, so we can deploy backscatter devices to some remote places. For example, to monitor pipelines across the country or monitor soil or environment conditions for smart agriculture. We can also deploy backscatter into the human body to track various biometrics. Recently, researchers proposed a system to utilize different existing signals like Wi-Fi, Bluetooth, Zigbee, and LoRa for backscatter communication. For example, the first system used a Wi-Fi signal to carry backscatter data published in SIGCOMM 2014 from Hitchhike in census 16 to Mockscatter in Mobius's 2018. The Wi-Fi signal-based backscatter systems were improved to support newer Wi-Fi protocols like OFDM and MIMO signals, respectively. Interscatter and FreeRider were proposed to use Bluetooth signal, and FreeRider can support Zigbee signal as well. Later on, several systems were developed to use the newer IoT protocol LoRa. However, there are two problems with using these protocols. The first one is the coverage in space domain. This figure shows LoRa's coverage in the US. We can see that the red spots cover very limited parts across the whole country. The figure on the right-hand side shows the LTE coverage of AT&T, which covers a majority of the US. The second problem is coverage in time domain. Let's take a Wi-Fi signal as an example. The first two packets can get through while Wi-Fi traffic is available. However, there is no lock for packets 3 and 4 because of the absence of Wi-Fi traffic. Since the 2.4 gigahertz Wi-Fi channel is shared with Zigbee, the Zigbee traffic during packet 5 could fail the backscatter transmission. The reason is that it is very hard for a low power tag to recognize the bandwidth and the modulation scheme of incoming signal. So the backscatter device can't choose the right backscattering scheme to reflect data. On the contrary, an LTE band is dedicated. There is no interference from other protocols or devices. And the best thing is the LTE signal is continuous. So The backscatter can transmit at any time without the need for a signal detector. To see the difference between LoRa, Wi-Fi, and the LTE signals in terms of traffic occupancy rate, we did some on-site measurements. The traffic occupancy rate is defined as signal presenting time over total time. This figure shows the measured traffic for a whole week in 3 different places: office, classroom, and a residential home. We can see that for more than 90% of time, the LoRa signal doesn't appear in any of the 3 locations because there is a very limited number of LoRa devices in use so far. For the Wi-Fi signal, we can observe a higher occupancy rate in an office than in a home or classroom. However, 60% of the time, the occupancy rate is only 20%, and 80% of the time, the occupancy rate is just 50%. In comparison, LTE has a 100% occupancy rate at all locations. To dig deeper, we look closely at the signal. This figure is a spectrogram of the Wi-Fi signal. Lighter color means stronger signal. The x-axis is the frequency, y-axis is time. We can see that the Wi-Fi signal spans 20 megahertz, but it is intermittent in time domain. There are many gaps among Wi-Fi packets, which is the reason for the low occupancy rate. The right-hand side is LTE's spectrogram. The signal is continuous. There are some little holes called PSS signals. We will talk about them later. Thus, we argue that for all existing Wi-Fi, Zigbee, Bluetooth, and LoRa systems, the bursty and intermittent traffic patterns make backscattering unreliable. Furthermore, the channel shared by many protocols and devices make backscattering even harder. Given the widely available and continuous LTE signal, we propose LScatter, which utilize ambient LTE signals for passive wireless transmission. The ubiquitous coverage in space domain and continuous signal in time domain can significantly help the adoption of backscatter systems. To let backscatter work with LTE, and due to the specialty of LTE signals, we have 2 major challenges: how to ensure critical information remains unmodified after backscattering, and how to modulate the LTE signal to achieve high throughput. Let's talk about them one by one. Since the cellular tower transmits LTE signals continuously, the signal is not packet-based. In time domain, the LTE protocol defines every 10 milliseconds as an LTE frame, and one frame is divided into 10 subframes. Here we show 6 subframes from 0 to 5. Each subframe is further divided into 2 slots and 14 symbols. In frequency domain, each row is corresponding to a subcarrier. The total number of subcarriers depends on the bandwidth, which can be from 1.4 megahertz to 20 megahertz. In the diagram, each small block can either carry data or control signals. The legend on the right shows the definition. Among all of them, there are 2 very important signals. The purple one is the primary synchronization signal, or PSS, and the light blue one is secondary synchronization signal, or SSS. These 2 signals are used to synchronize the receiver with transmitter. So the receiver obtains the starting point of fast Fourier transform. These two signals are very special Z-of-true sequence, which can be easily recognized by the receiver. If we destroy these two signals, the receiver will not be able to conduct demodulation. So we want to avoid touching these signals while backscattering. To do this, a naive solution is using a high power consumption module to recognize the signals. However, a low power tech can't afford this. Instead, we found some features of LTE signals and utilize a low power circuit to do a coarse synchronization. Specifically, we found that no matter the bandwidth of LTE is 1.4 megahertz, 10 megahertz, 20 megahertz, or other configurations, the width of the PSS is fixed at 930 kilohertz. Most importantly, the PSS periodically appears 2 times a frame, which means every 5 milliseconds. Then we designed a low power circuit to locate the PSS signal to achieve synchronization. The first stage of the circuit is a matching network, which achieves impedance matching to maximize the power of incoming signals. Then a passive filter is used to suppress high-frequency components. If you recall, the PSS we are looking for has a period of 5 milliseconds, which is 200 hertz. After the filtering, we can visually see the spikes corresponding to the PSS. Instead of using a power-hungry ADC to sample the signal, we wanted to use a low-power comparator. To use a comparator, we need to generate a reference signal, which is achieved by a simple averaging circuit. The circuit averages the signal over time and feed it into the negative electrodes. The voltage comparator compares the filtered signal with the reference and output a square wave, which is fed into FPGA for PSS signal determination. Then we move to the second major challenge, how to modulate the LTE signal to achieve high throughput. To embed backscatter data into ambient signal, a tech tunes the phase while backscattering. Let's first consider an existing method used in many OFDM-based Wi-Fi backscatter systems as an example. In this figure, each column is a symbol, each row is a subcarrier. The backscattered signal with 0-degree phase change indicates data 0, the light blue color, and a phase change of pi indicates data 1, the red color. Given a symbol duration of 4 microseconds for Wi-Fi, the phase is changed every 2 symbols, which yields the throughput around 60 kilobits per second. If we use the same technique for LTE backscattering, since the symbol duration is much longer, the throughput will be reduced dramatically to a few kilobits per second. To solve this problem and increase the efficiency, we propose a basic timing unit modulation scheme. In this scheme, rather than change phase every 2 symbols, we change the phase at the basic timing unit level. The basic timing unit is corresponding to the LTE signal bandwidth or clock rate and much shorter than symbol duration. Then, at the receiver side, we will see phase changes on different subcarriers. Different from the previous scheme, in which the phase change is the same across the subcarriers. By doing this, we can achieve high throughput of up to 13 megabits per second. We also faced other challenges like cyclic prefix and intersymbol interference, demodulation error, and determining modulation offset. For sake of time, I will not introduce this into details. Please refer to our paper. After overcoming all these challenges, we implement the backscatter on a customized PCB with low power FPGA and RF switch. We use USRP with the SRS LTE library to implement the eNode B and UE, which are the transmitter and the receiver respectively. Then we evaluate the system in 3 different scenarios: a residential home, a shopping mall, and an outdoor scenario. To compare with LTE backscatter, we also implemented a Wi-Fi based backscatter system. Let's first take a look at the throughput for each hour during a day of Wi-Fi backscatter. We can observe significant fluctuation and outliers. From afternoon 16 to 21, we can see a relatively high throughput. All of this are because the intermittent traffic of the Wi-Fi system. Move to LTE, we can see resilient performance throughout the day. Furthermore, the average throughput of LTE backscatter is 2 orders of magnitude higher than that of Wi-Fi backscatter. To understand the underlying reason, I'm going to show the traffic occupancy ratio across 24 hours in a day. We can observe that LTE always has full coverage, while Wi-Fi traffic totally depends on the usage. During rush hour like afternoon and evening, higher traffic occupancy rate leads to higher throughput. After midnight, the poor occupancy rate will make backscatter useless. As I mentioned before, LTE has different bandwidth configurations. With the generic design, L-scatter can support anywhere from 1.4 MHz all the way to 20 MHz, and the throughput of backscatter communication is proportional to the LTE bandwidth. The figure on the right-hand side shows the communication distance between tag and UE, the receiver, versus communication distance between tag and eNode B, the transmitter. When the distance between tag and the transmitter is 2 feet, the tag can be 230 feet away from the receiver. When the distance between tag and the transmitter is 24 feet, the tag can be put 160 feet away from the receiver. We also note that with the rear cellular tower, which has much higher transmission power, L-scatter can achieve even longer communication distance. Then we show how L-scatter impacts the original LTE signal. This figure includes 3 different bandwidth configurations: 1.4 MHz, 5 MHz, and 20 MHz, with or without a backscatter tag. For example, the red and the blue curves shows CDF of 1.4 MHz bandwidth with and without backscattering, respectively. We can see that backscatter introduces negligible impact to the original LTE communication because the signal is shifted out of the original band. To conclude, in this paper, we considered a new aspect of backscatter communication: ubiquitous coverage in time and space domain. We also demonstrated that it is possible to backscatter the constantly strong and widely available LTE signal. And we extensively evaluated our backscatter system in 3 different real-world scenarios.